Uniform circular motion, a pretty glorious topic to be sure. You can see on the left, or sorry, on the right, there's a guy twirling a little rock around a circle. On the left, there's an overhead view of that same thing. I use a square instead of a rock because it's easier to draw. It's going clockwise in that circle around. You can see the string in the center of it. Okay. You can see the velocity of that rock is forward or up in the direction of the picture. Okay. And you can see that there's a change in velocity. It's going to move, it's going to be pulled toward the right by the string. Okay. And when that happens, that's going to make the new velocity at a diagonal. And that's going to keep the thing in the circle. And that's going to make it go all the way around the circle. Because that's going to keep changing as it goes around the circle. And that's going to keep it moving in that circle, keep it going around and around and around, so that the velocity magnitude can stay the same, but the direction is different all the time. That's why it's accelerating. It's accelerating because it keeps even if it keeps the same velocity, because it's got a different direction all the time. You can see there's a change in velocity, and it's toward the center of the circle. That's the direction of the change in velocity. We saw that earlier. It's called a centripetal force or a centripetal acceleration. It's center seeking. That's what it means. It's moving toward the center. That's all we're looking for there. Now we're going to do a derivation of where centripetal acceleration comes from. You can see I drew a line for that, and it shows the radius r, and it's got the first velocity. If I move a little bit further, this time we're going to move counterclockwise as we move. You see I moved a little bit further in an arc, and I have a new velocity, v2. Okay. If you look, it has the same magnitude, actually. I drew another line at the radius, and I showed a theta in there, too. And I called the arc length s. Now, I can't draw a small triangle because, well, it just wouldn't be visible to you. But assume it's a pretty small triangle, okay? Which means that the length of S is pretty close to the length of a triangle. So it looks a lot like an isosceles triangle. Imagine that if you could. It helps a lot. Okay. Now, I took those two velocities, v1 and v2, and I put them side by side. Now, if you look, I didn't line them up real well because ideally, if you saw them, they would be like the 2 points would be together. Anyway, I tried my best. I'm sorry. And then I put a little line to represent delta V. Delta V should point a little down toward the center. If I drew it a little better, you can see that. Okay. And what's interesting about those two velocities, and if I do it right, you'll notice that the angle of those is the same. I swept through the same amount of angle in both of those. And that the two velocities are the same. Okay. The two velocities should be identical. Like if I extended those two velocity vectors out, I end up making the exact same angle. And the two velocities are the same. I didn't change that. Okay. So what that means is now I have two triangles, both with sides that are both the same and with the same angle in the middle. So they're similar triangles. They're not congruent, they're not equal, but they are similar triangles. And I can say some stuff about similar triangles, like that any ratio of the two sides is going to be the same. So I can do that. So I can say that the small side, s, over one of the long sides of the radius is going to be equal to the same thing on the other triangle. Delta V over V. I moved it over to the side. It's a little easier to see. So again, the short side over the long side of both of those triangles will be similar. Again, because they are similar triangles, not congruent, just similar. Now we're going to play a little math and magic and move stuff around. I divided both of those expressions by t. Because, well, I'm going to need to. And I'll explain why as we group the things along. Okay, so I just grouped them out. So I have s divided by t and 1 over r on the left-hand side. Okay. And then I took the delta v and I divided it by t and put 1 over v. Okay. I wish I'd grouped the two sets of parentheses the same, but it just didn't work out the same way. I'm not sure why. Okay. But it didn't. Okay. But you can see that I just grouped them the same. Now I can replace each of those expressions not in the parentheses something else. Okay, the distance that it moved, s, divided by the time that it moved, just another expression for velocity. Okay, so I can replace that with velocity. Okay. And the expression, the change in velocity divided by the change in time, that's just another expression for acceleration. So I can put that over there too. Okay. Now I'm going to multiply both sides by velocity to get the acceleration by itself. And I get that a equals v squared over r. That is the expression for centripetal acceleration. And if you look at it, you can see that even the units turn out correctly. A velocity would be meters per second, so squaring it would be meters squared over second squared. Divide that by the unit for distance, that's what radius would be. Those would be meters, and you get meters per second squared. So the units turn out correctly as well. So it turns out to be a pretty good deal, and it describes it pretty nicely. That's the expression we're going to use for centripetal acceleration. I think you've seen it before, but just in case, that's where it comes from. There's another version of this that's helpful. If we want to solve for centripetal acceleration using period instead of velocity, we just have to substitute some things in. We have to remember that the circumference around a circle is 2 pi r. So that means that the velocity is going to be distance over time. 2 pi r, the circumference around, divided by t, the period to go around the circle once. If we plug that in, then the centripetal acceleration is going to be the quantity, 2 pi r, over period, squared, divided by r. Okay. Then we got to move some stuff around. I squared all the things that were inside there, 2 pi squared r squared over the period squared, all divided by r. Then I'm going to divide out an r from the top term and the bottom term. And I get that the acceleration is 2 pi squared r over t squared. And you can see that even that takes on dimensions that are the same, because 4 pi squared obviously have no units, r is a unit of meter, and time is a unit of second, so it's meters per second squared. You can use that acceleration to describe all kinds of motion. Many times it's used to describe gravitational force, a number of g's or something like that. And use that expression to describe any form of acceleration moving in a circle as centripetal acceleration.